Continuing from the previous lecture slide, we are going to continue to the Python demonstration where we can visualize the phase diagram of the CO2 and the viscosity and density changes with a varying temperature and the pressure. So let me get it started. Please go to the I class as always. And in the current week course or week 5, we have 2 more further on top of the lecture note. So in the first folder, we have a Python script that we need to run the demonstration. And then in the second folder, we have several papers that we've been using for this formula for phase diagram or the density or the viscosity changes of the CO2. So if I go to this paper folder, I'm going to open the first 3 papers. So in the first one, in this paper, it has very many pages, but this is specifically referred to visualize the phase diagram. So I will just skip that part. So if you scroll down, for the CO2, it has some other basic formulation for the CO2 property. And from chapter 3, it has information about the triple point temperature and the pressure. And this one, allegedly, this one is the density of the liquid in the triple point, and this is the density of the gas in the triple point. So we have 2 different density in the triple point. And if you scroll down, we also have critical temperature, critical pressure, and critical density. The rho is indicating the density, P is pressure, and the capital T is temperature. And their units are Kelvin, megapascal, and the kilogram per cubic meter. Basically, they are SI unit. And from here, we have melting pressure, which are given here. If you scroll down, we also have sublimation pressure, which are given here. And also lastly, vapor pressure, which are also given in the next page here. So basically, if we follow these equations from the phase diagram, where y-axis is the pressure and the x-axis is the temperature, and we had 3 different lines. So sublimation curve, and after this we have a triple point, and after the triple point we had a melting curve, and also we had vaporization curve, and this is the critical point. So this is C, this is the T, and in each section or the region we had a different phases. For example, we had a liquid, gas, this was solid, liquid, and gas. And anything whose density, whose pressure and the temperature is exceeding this critical point, and this is called a supercritical state. Supercritical state. So to plot this phase diagram, we need to make this first sublimation line, and we also have to have this melting line, and lastly we have vapor curve. So we need these 3 lines, and these 3 lines are provided in this paper. So that's first thing that we want to do. So please go back to the I class and go back to the folder where we have the Python script. And unlike the previous demo, now we have 2 different Python script. One is under the Jupyter Notebook, and the second one is just under the extension of the Py. So I'm gonna download these 2 files. So I'll just download it, and I'm gonna have some working directory where we can work with. Okay. Please give me a second. So I just had this folder where I just copy and paste these two files that we have, and from here we have to open the Anaconda. So open the Anaconda navigator. Even though these for me equations and then correlation relationship seems a bit complicated, we already have that into the Python script. So and also this Jupyter Notebook is ready to go. So if you just follow the sequence of the exclusion, then you will have all the figures that we've seen in this demo. So but once you are doing this on your own, then you may have to investigate how each functions or the command or the keyword works seamlessly together so that we can get the final visualization. So go to the environment, and from there, open the terminal. And once you open the terminal, I'm going to move to the directory where we just copy and paste the two Python script. And then I will just run the Jupyter Notebook by typing Jupyter Notebook. And hit the enter. And it will be open. So these two are the files that we just downloaded. First of all, in this Jupyter Notebook file, we have the same format as before. But in the second file, which is CO2 underscore EOS.py, if you open it, you can find it's just simply a text, a lines of the text that are following the Python languages. By the way, I had a help from Jinu and Unshil for this Python script, and we've been working this on together during the last summer research internship for the undergraduate, and I really appreciate the help from these two. And and also we have some list of the paper that we've been referring to, and here we have some main description. So as you might know, any script after the this pound is actually commentized. So anything here that are be ignored in Python, this is just simply to write down our description, because it's good to have some good name or some description and then the name of the authors. And then when I was updated the last time, so that's why I had this. And after this, we have a series of the different functions. So these are the functions that we need. For example, we had a triple point and the critical point, melting pressure, sublimation pressure, vapor pressure. And the typical grammar for the function in the Python, it goes like this. So it starts with a DEF, and then we need to have a name of function. I will just call it the function. And we need a round and colon. So this is start. And anything below, we have a computation that we have for this function. And then as a result, we also return the outcome. So in case we need some input into this function, then we can provide an input in this location. But if we don't have any input that is required, then we can simply make the empty within the round. And within this part, we are gonna do some computation. After we will say the output is equal to some formula and that's how we can get the as a return we can get from this function. And after we define this function in Python, we can call this function repeatedly every time we need to use. So, and the function call goes like this. So if it doesn't have any input, then we don't provide any input, but we still have to provide the round, opening round and the closing round, so that it's calling the function. So this is how it look like. For the triple point, we already have the value for the triple point. So pressure and the temperature, and also critical point, we already know it, so we don't need any input. That's why it's empty. But once we do that, then we return in the sequence of the pressure, temperature, and the density, and pressure, temperature, and the density. So these two function is to get the triple point and critical point pressure and temperature of the CO2. And these so basically, okay, I'm gonna get a snapshot of this. So okay. So here, melting pressure. This melting pressure is for this line, and sublimation pressure is for this line, and lastly, vapor pressure is this line. And as you might know, this curve is a function of the temperature. So with a given temperature, we have to calculate their corresponding pressures like this. So we have to get the pressures that are on this curve, and also likewise we have to get the pressures with a given temperature to make this line. So that's why, unlike the previous critical point and the temperature, now we have input that is temperature here. So we have one input that is temperature and temperature and temperature, and these one are given and provided in the paper. So this is how we calculate, and as a result we get p underscore p, p underscore sub, p underscore ps, and then we are going to return this as an output of the wave function. So this is what it does. So we are going to use this repeatedly. And also for the viscosity and the density, now we have two inputs, which are the pressure and the temperature, and that's why we have two. You can ignore the last one for now. So the pressure should be given in the bar, and the temperature should be given in the Kelvin, and the outcome will be given in the centipoise for the viscosity. And for the density, the outcome will be given in the kilogram per cubic meter. And we have the complicated correlations that are being provided in the paper that we're referring to. Okay, this is it. This is the information that we have in this Python, like a CO2 underscore EOS. And just be sure that you have this Python script in the same location as this Jupyter Notebook, because when we run this Jupyter Notebook, then we need to find this Python script, and as a rule of thumb, we have to define the exact location for this additional Python script. And if it's in the same location as the Jupyter Notebook, then they can easily find where they are. So I just open the Jupyter Notebook again. So here we have explanation. In this demonstration, we were estimating EOS, density and the pressure of the CO2. Here we have 3 different papers they've been referring to. For the phase diagram, we use this one. For the the density, we use this one, and the viscosity, we use this one. And lastly, we haven't covered everything, such as the thermodynamic property. But if you are interested in the thermodynamic properties of CO2, then you can also refer to this paper so that you can make your own function to make that work. Let me get it started. So first thing first, we have to import some packages. Today we are going to use the NumPy array. NumPy is a packages to manipulate a series of number. That series of number is called array. And the second and third, this is for the Python visualization. So for now, you don't have to change anything, and you can just code it in the same as this. And so just be sure that first one is for the array, and the second and third one is for visualization, especially for the last one. This is for the 3D visualization of the response surface of the density and then viscosity. And here we have a very interesting name of the package. So this is not open source package, by the way. So what it means, so we have the Jupyter notebook and this location, and in the same folder, this means we are going to looking for the same CO2 underscore EOS Python script, which is given here. And from there, we are importing these functions. So if you remember, triple point are given here. So that's how we can call the triple point. Likewise, we can also call the critical point, sublimation pressure, vapor pressure, melting pressure. Okay, melting pressure, sublimation pressure, and vapor pressure. And the name are supposed to be exactly the same. So the name here should be the same as the name in the Python script. Otherwise, because in this Jupyter notebook, it will open this Python script, and then they will look for the name, exact function name. Then if they cannot find such function, then it will return the error. So they cannot run this. So I've hit the enter. So it runs successfully, but somehow I made some mistakes, such as I made a critical point with a capital P and the capital C and capital P, which is not identical to this one, because the Python is case sensitive, so they can tell the lowercase and the uppercase. The name here is a lower K and the lower P, whereas we are looking for the capital P and capital C, right? So in this case, yeah, they cannot find this function. So we have an error message that says we cannot import name this function from here, and these specific files are actually given in the same working directory and the same the name of the Python script that we have, and that's because we simply don't have such name in this Python script. So I will just return it back, and now everything is okay. And by using the triple point, the critical point function, so this triple point, it returned the pressure, temperature, and the density, and the critical point also return the pressure, temperature, and the density. So we can get pressure, temperature, rho, pressure, temperature, rho. So and then using this print statement, we are basically printed out what the triple point pressure and the triple point temperature here, and their corresponding unit as well. And then the second part, this is getting more interested, I think. What we want to do here, we want to visualize the phase diagram of the CO2 by on ourselves. So first, we have to have the intervals between the 200 and 400 kelvins, which means, if I may go back to the paint here, okay. Okay, it would have been nicer if I copy and paste it earlier, but anyway. So we have this phase diagram, and to enable this phase diagram work, then this is 200. Let's say this is 200 Kelvin, and this is 400 Kelvin. To make this line, then we have to split every intervals between 200 and 400. So we need to get this line. That's the first step, which is having the interval between 200 Kelvin and the 400 Kelvin. And please note that this sublimation curve only exists between the 200 and then triple point temperature, and this melting curve exists after triple point until like a 400 Kelvin, and this evaporation curve or the vaporization curve, the interval exists between the from here to the critical point. So so first we have to get all the intervals, And from the intervals, we have to get three different subsets. The first subset goes like this, and the second subset is between the critical pressure and the temperature. Critical temperature and the triple point temperature. And then lastly, for the this melting curve, we have to get from the triple point temperature until the 400. So we need to have like three different intervals, and that's what we are gonna do. In the second step, separate the intervals for three different lines, and then we have to calculate using the function that we had, and then plot everything into one figure. So this np dot linspace is to get the interval. Starting from 200 and at 400, between these two, we are gonna split with a 1001 intervals. I will just give you some brief examples. So if we split this by 11 intervals, then if we print it out, then it will be 200, 222, 220, 240, and so on to 400. But if we increase the number of intervals more, then it will split the in a smaller number, and of course, if it increase the 1001, then it will split every 0.2 intervals of the temperature. So this is the entire temperature intervals, and from there we have a three different separation. So the first separation is for this first one, which is the sublimation curve. And this sublimation curve, it's below the triple point temperature. So from the interval, we only select the temperature that is lower than the triple point. That's what it meant. So this means T intervals before the triple point. And also for the green interval, which is the after triple point, we only select the temperature interval that are exceeding the triple point. So this is triples after triple point, intervals after triple point. And then lastly, for the vapor curve, we need to get the interval between the triple point and then the critical point. So this should be TT, not TC. So okay. So this is what it does. So rather than the triple point, but smaller than critical point, critical temperature. And by using the function that we already defined in here, I'm not gonna review the details. It's okay for now. You can use it repeatedly. We will get the sublimation pressure, melting pressure, and the vapor pressure. So you just calculate it. And then lastly, now we have to visualize it. So plt.plot is to plotting purpose. So in the last demonstration, we used the pandas for the visualization, but internally pandas are also using the plt. So plt means plt.plot means it will take x and then y. So if so, then it will create the plot that looks like this. So x variables in an x-axis and y variable in the y-axis, then it will create some line curve. And the label is to name the name of this line. So for example, you can name it it's like a line A. And in case you have more than one line, so you may have a 2 or 3. So in that case, you can name it in a different letter, like a C or B. So if you labeled it, then later on we can say that this green line is for B, and this red line is for C, and the black line is for A. And basically, this is the legend of the line. So that's why we have this label. So back to the Jupyter Notebook, we have 3 different lines. So let's see. The first line is sublimation curve. So we provide x, which is the temperature interval that are corresponding to the this sublimation curve, and then y, which is the pressure, are given in the second input. Likewise, we also have a melting curve, vapor curve, and we also named it in this manner. And if it's not a series of number. Instead of this line, it will also plot a point. So we are gonna make the critical point and the tipper point. And this indicate the color and the marker. So we are gonna use the asteroid shape marker that are colored by the red and blue. So we are gonna have the red asteroid mark for critical point, and then the blue asteroid mark for the tipper point. And of course, we labeled it like this. And this is to make the legend in the end. So this other rest is decoration. So we have one big title, x-axis, y-axis with a given unit. It's very important to have the unit. And we are going to have the background grid. And if you go back to the lecture note, you may find that the y-axis of the phase diagram were given in the logarithmic scale. So if I may quickly show you, so we had this pressure in the logarithmic, because it increased by 10 times, 10 times, and 10 times, 10 times. So that's why we want to convert this y-axis in the log, and this is what it does. And we have phase diagram here. So basically, this diagram and this diagram are supposed to be identical. So what do you think? I assumed this figure shows pretty nice phase diagram as the lecture note. Why do we have to visualize it? Visualization is not only the purpose of this exercise. Once we have this 3 different curves, we may need to have some other logics to determine their corresponding phase. But basically, from here, we can distinguish the phase of the CO2 with a given pressure and the temperature. So once we have a temperature, then we can categorize where they belong. And once they have the corresponding temperature, then we look for their corresponding melting curve and the vapor curve. And depending on whether the pressure is larger than this one or the lower than this, and larger than this one and then lower than the green line, we can tell it's a solid, liquid, and gas. And also we can compare it with a critical point so that we can tell it's a supercritical region. So so this is our first exercise, and we will move on to the next. And for this one, we are gonna have these density changes with respect to the pressure and the temperature. And please note that in this paper, they specifically use the bar as a unit for the pressure instead of the megapascal. So we are going to use bar. So that's why in the beginning, we have a unit conversion between bar and the pascal. And again, 1 bar is equal to 10 to the 5 pascal. So 10 bar means 1 megapascal. So temperature interval, it's varying between 300 and 420. So we have the interval of the 300 and 420, and we will split by 1001. For the pressure, same way, it will vary from 25 bar to 70 bar. So I use a slightly lower number than a 70, but so this is 70 megapascal and this is 2.5 megapascal, and we want to convert this into the bar. So that's why we multiply by 10. So that, yeah, I just have the number in a megapascal, but they will be in bar in the end in this pressure interval. If I may have one more comment on this. So let's say we want to visualize something on this figure. So we just had intervals for the temperature. We just had intervals of the temperature, which are between 300 and 420. And we also had an interval between 700 bar to it was 25 bar. So now we have these two. But to make this 2D continuous or the entire response surface of density changes in CO2, we have to make the mesh of the intervals, which means from here, like a chessboard. Okay, let's say we only had a 3 intervals, so 1, 2, 3, maybe 4. And we also have another corresponding interval in the temperature 1, 2, 3, 4, 5, 6, 7. Then what we ultimately need is every point or the combination of possible interval between the pressure and the temperature. We have to get these blue dots. So, and these blue dots it's called a mesh. So we define the interval in the one-dimensional axis for the temperature and the pressure, and by combining these two intervals, now we have to make these meshes so that we can get a full extensive range of the possible pressure and the temperature combination, which are shown in the blue dots here. So that's what we need to do. So if you go back, so we get the interval for the pressure and the temperature, then we are meshing it. So np dot mesh grid, pressure interval and temperature interval, we will have the pressure mesh and the temperature mesh. So it will be 2D matrix, and this will be also 2D matrix, and that are corresponding their own pressure and the temperature in every meshes. And we can provide it to the density underscore CO2 function. And I just had a bit of the more modification so that it can be compatible with a mesh. The original function wasn't working with a mesh, so that's why I had a little bit of the modification from the our last summer research internship students' work. So we provided pressure and the temperature, and now we will have a 2D matrix of the density with a changing pressure and the temperature. So if we run, it runs really fast, but given that this mesh has about 1000 by 1001 by 1001, so it's about 1 million point. So we iteratively calculate the 1 million density of the CO2 in this cell, and it worked really fast. And the numpy is specifically for this type of the array. So once the number get a large, the dimension of the number is large, then the numpy is highly optimized in a way to make this such computation work in a really short time. So so that's how we can get the outcome almost spontaneously. And then lastly, we will have the figure. So this is for the 3D figure. So this has slightly different format as the 2D, but it's okay. So first of all, we are going to have the figure size. So I found that the initial figure was a little bit too small, so I just enlarged it to 5,5. So the width and height are given here, and we are going to have in the 3D, and from the 3D we will have this surface and x, y, and the z, and then we will color it by the color scheme that is called the jet, and the jet is the same color scheme as this one. It starts with a blue and end with a yellow red. And this is not recommended for typical presentation. This is not my favorite color scheme because it's not colorblind friendly. In Python, as a default, they use different color bar or the color scheme, which is called the Viridis, and I prefer Viridis much more than the jet. But anyway, for now we will just start to use the jet. The jet is provided, and the decoration X bar, X label, Y label, and the Z label, you know what it means. And we have to. I found that to make the same figure as the reference, we have to flip the x-axis because so it's getting large in this direction, and this is also getting large in this direction. This is not typical 3D visualization. So that's why I had to flip the x-axis. So this is minor changes, so you don't have to care much of it. And then lastly, we also can provide their color bar so that we can indicate the numbers or the value of each color. Okay, so if you hit the enter, then we have a response surface of the density. So we have a color bar. So and it's horizontally located. So and then the reddish means it's about 1000, and the bluish is about 0 or larger than 0. So Jupyter Notebook by itself plot everything in into the Jupyter Notebook. So once it's plotted in the Jupyter Notebook, it's that. So we can copy it from here, and then maybe you can copy and paste it your PowerPoint or the anywhere you want. But it's not interactive. But if you want to have an interactive figure, then please follow this command. So instead of the inline, you can have you can say percentage mark matplotlib and tk, and if you rerun it, then you will have a pop-up window with a figure, and in this figure it's alive, so you can rotate the surface as you want, and this is how you can play with it. And of course you can also save this as a figure, or you can also zoom in or zoom out. So if I may zoom in, then yeah, this is how it looked like. So we just finished the density, and we did the same for the viscosity. It had a different ranges, and that's because this particular formula only work within this range, and this particular formula also work within this particular range, and these range are given from the paper. So I will just run it, and this is how we can get a viscosity curve, or the viscosity changes with respect to pressure and the temperature. So from 0.02 minimum to 0.16 maximum. And if you compare it with this, if you have a right angle, then I think these two figures are about the same. So so yeah, this is it. So this is what I prepared for today. And once we have this, what we're gonna do? So what we are gonna do? So we are gonna use this function iteratively. So given that the CO2 is not incompressible, so it's compressible. So when we transport from the terminal to the endpoint, the pressure will be varying in the pipeline. And once the pressure changes, that means the viscosity and the density will be changing. And we have to calculate that viscosity iteratively so that we can get the accurate pressure losses from point A to B. So in the next lecture, we are gonna review what the Reynolds number and then the Moody's chart, friction factor, so that we can get the friction pressure loss. Once we do that, then we can combine that concept with these functions so that we can have a numerical workflow to calculate the pressure changes for the CO2 transportation. That's gonna be our next objectives. And I will stop here for now, and thank you for listening. And for those who have any questions, please reach me out or reach out the TA. We have wonderful TA. We are very willing to help you. So please don't hesitate to contact us. Thank you.